Okay, hey folks, we're getting into Module 3. We're finally tapping into our content on thermodynamics, so we're going to start with the first law. So as you can see, Module 3 here is pretty massive. We're going to take a couple of weeks to get through all of these learning goals. So we're going to start simple by just looking at some definitions and foundational concepts introduced by the first law of thermodynamics. So to get started here, let's take a look at some definitions. So the first thing to discuss is an intensive property. So that is a property that is independent of the amount versus an extensive property which depends on the amount. So things like temperature and pressure are good examples of intensive properties. When we talk about the temperature of a sample, generally, it doesn't matter how much of that sample there is. Extensive properties, good examples are things like mass and volume, right? The more of a thing that I have, the more mass and volume of that thing that I have. So something interesting happens if we take two extensive properties and divide them by each other. So for example, if I take mass divided by volume, two extensive properties, I get density, which, as it were, is an intensive property, right? So we're going to see this happen throughout our chapter. If we take an extensive property divided by another extensive property, that's going to turn it into an intensive property. Okay, work is a force acting over a distance, and we've talked about this equation before at the beginning of this class as well as in physics. Energy is the capacity to do work, and we're going to use a big capital U to denote the internal energy, which we'll discuss soon. Heat gets the letter Q, and that is the transfer of energy between a system and its surroundings. So heat is a process, not a thing. So we often, talk about heat as if it were some tangible thing, but it is a process. And hopefully these two definitions you recall from your other classes, exothermic and endothermic. So exothermic, a process that releases heat out to the surroundings, and endothermic, a process that acquires heat from the surroundings. Okay. So let's keep going. A few more definitions for the types of systems we might have in thermo. So let's write that down. Types of systems. So we could have an open system, and I'm going to use SYS in this class to abbreviate system. And outside of the system, of course, are the surroundings, which I'll abbreviate as SIR. So in an open system, mass and energy are free to exchange between system and surroundings. And of course, it could be exothermic or endothermic, depending on which way it goes. In a closed system, so let's put that down, we've got system and surroundings. The energy may exchange between system and surroundings in a closed system, but mass is fixed. So we can't put any new mass into a closed system or take out mass. And finally, in an isolated system, both energy and mass cannot exchange between system and surroundings. So a truly isolated system is extremely rare. Even like the best adiabatic systems or the best insulating systems are still not perfect. Okay, so it is extremely rare to have a truly isolated system. And then for our final definitions that we're going to go over, state functions and path functions. State functions are always represented by capital letters. So that's an easy way that we can tell if we're dealing with a state function. And they are path independent. So for example, hopefully we recall the delta, right, meaning final minus initial. Well, in this case, when we look at these two different computations, taking just the true final minus initial versus integrating this function over some initial and final condition. If these two things are equal, then we have a state function, right? So the delta x gives us measurable changes. The dx gives us infinitesimally small changes described by calculus. So path functions are usually, and not always, but sometimes we try to be consistent as best as we can. Path functions are usually represented by lowercase letters and are path dependent. So in other words, if we look at this integral, and here I'm noting that that is a path integral, so it depends on the way in which we integrate it. It depends on the path that we take. This is not necessarily going to be equal to the final minus the initial. Or in other words, dx does not equal delta x for a path function. So some examples of path functions that we're going to see right away here in the first law: heat and work. And for the state function, internal energy U. So big capital letter for internal energy and lowercase letters for Q and W. Let's see. Okay, folks, that's it for this opening video going over definitions. I'll see you in the next one.